myself. Yes. Okay. All right.
Ask the AI to write some code, and then you can get us to tell you why it's wrong.
So yes, I could have the AI write some code and tell us, have it and explain why it's wrong. Maybe. AI writes some wrong code. Okay, so let's take a look at, there was a couple of slides that I wanted to go over that I failed to cover, and that starts here, futures in C++. So theoretically, you can program in other languages besides Java, and C++ is one of those languages. So C++ has, you can do a pound include future, and then you can say std future int, and then you could say standard async, standard launch async, fib, and then n-1. So you can write a Fibonacci in this fashion using futures in C++. And if you run it, it kind of looks like this. And at least when I last ran it, it got to about Fibonacci 19 or so before it died, before it became blocked. Alternatively, so if you want to do the clever thing, right, where you do the optimization for n greater than 23, you use the parallel computation. Otherwise, you do the serial one. Then you can get up to fib 41 or so. Alternatively, there is a package which you can use called HPX, and HPX is developed at LSU by the Stellar Group here. And you can get the source code at this link. And it provides a distributed futures-based computation for C++. So they're really, the Stellar Group is, I got the hiccups. Stellar Group is aiming to replace MPI with this. They want you to be able to use a high-level language like C++ and futures to send data across the wire from one machine to another. And it's possible using this package. Also, unlike the standard package, they have a .then function, which works much as the then run does in Java. One of the interesting things about HPX is that when something blocks, like if you do a future get or you call a mutex lock, it actually has special code in there to switch the context out, so that your thread pools can continue to run even though you're using mutexes, because, as I say, they just pop that waiting thread out and put another thing in. So there's some clever magic going on behind the scenes to try and make that work. Of course, you can still deadlock and all those other things, but you can write, mutex codes with mutexes and gets in them, and you can run on a thread pool with one thread in it, and it will run because it's able to switch in and out like that. So future, if you use HPX, the code looks almost the same, right? You have some different, instead of pound future, you've got HPX HPP and HPX main, and then you have HPX future and HPX async instead of std future and std async. But otherwise, everything stays the same. And when it runs, you can get to a larger Fibonacci number. Any questions about that? If you're a C++ programmer looking to do parallelism, I would encourage you to check that out. Okay, so the actor model. This is sort of a little detached note on these sorts of things. The actor model is a model of computation. It's a way that you can sort of envision a computation happening. And the actor model says that each actor has a work queue, and each actor runs has a single threaded access. So each actor is doing one thing at a time. And in response to a message, an actor can change state or create more actors or send more messages, right? And the concept here is they're envisioning actors as existing in a distributed environment. Um, and the amazing thing about this is because of the way it's designed, right? You can't deadlock or anything. You only have the only lock you have is the actor itself does one thing at a time, and you can't, join the actors together. You can't multi-lock kind of thing, and everything is asynchronous. It's kind of pretty. It's kind of popular. A couple of different computing platforms are based on it. Um, let's see. So if you want to do a return value in an actor, you have to use a future because, again, everything is asynchronous. And in principle, you can move the objects, right? So you can send a message to an object, to an actor saying, move from this processor to that processor, and it can pack up its data and go over there and start running over there. You have to do some kind of address forwarding or something to make it work, but it's possible to do. There is a package from UIUC, University of Illinois at Urbana-Champaign, that does something similar to that. It's Charm++, and it's been around for about 2 decades. It's got very it's got a boatload of papers attached to it. So that's a very interesting thing to know about in the parallel computing space. Any questions?
Do you have any code showing actors?
I do, and we will see some. Baron. Well, technically this is chapter 16, but these couple of slides aren't anything in there. It's related to chapter 16. Let's put it that way. Yes, Tristan.
The Charm++ library.
So the idea behind the Charm++ library is you want there's a couple of different things that they can do with it. So first of all, they can over decompose the problem, right? So that means you break it up into more tasks than you have processors, and depending on your workload, you can shuffle the work around. Because the actors are potentially mobile, you can move them from a heavily loaded processor to a lightly loaded processor and speed up your calculation. And the asynchrony means that you're potentially making better use of your processors, right? Because if you're doing locks or gets, if you're doing anything that's blocking, you're spending a lot of time sitting doing nothing. If you look at many MPI codes, you will find that most of their time is spent in something called MPI wait, right? So the move to asynchrony in codes like HPX and Charm++ is an effort to try to spend less time waiting.
So it's basically able to it allows the program to be more flexible in first computing.
Right. It allows it to be more flexible as to where and when tasks run.
Makes it go faster.
Right, because it's going faster because you're wasting less time. It's kind of like imagine how fast you could get through your classes if you didn't have to spend time waiting in line outside doors and whatnot. Any other questions?
Can we ask questions for the whole chapter now?
Yes, please do.
Okay, so
Do you have a slide number?
balance for the Fibonacci sequence data. It's slide 47.
Okay. Okay, so this isn't specific to Fibonacci, right? This is for anything really. So what we're saying is, if the time to run on P processors is guaranteed to be greater than or equal to the time it takes to run on one processor divided by the number of processes, right? You can't do faster than perfect parallelization, in other words. And likewise, the amount of time on P processors can't be less than the time it takes to run on infinite processors, or at least it really shouldn't be, right? I suppose in practical terms, You can find out when you go to scale your code, you find that above a certain number, you start to slow down again because you're under decomposing a problem. But in principle, that, you know, if the amount of work doesn't change, that shouldn't happen. Does it make sense? All right. Yes, Ryan.
Could you walk through the pseudocode on page 125?
125. I love that everybody knows slide numbers
You just know that slide number.
because he was studying it and he got lost there. That's how. Okay. So, all right. So this is the stealing work sequence, right? So what we do there is we read the old top and the old stamped because we're using these stamped markable references. And we're getting a new top and a new stamp. So the new top is going to be the old top plus one. We're incrementing the top pointer. And then the stamp, we're also going to increment that. All right. And we might not use those values. But now we're going to say if bottom is less than or equal to old top, return null. So if bottom is less than or equal to old top, what does that mean? It means that there are no tasks in the queue, right? Because you have the top pointer. So you picture the queue as starting from 0 at the top and counting downwards under the ground, whatever, right? And you have old top, the top pointer has a lower number, but it's higher up than the bottom pointer, which has a higher number but is further down, right? Follow what I'm saying? Okay, so you see this counter here on the side? It counts down, right? So the top pointer is visually above the bottom pointer, even though the top value is smaller than the bottom value. It's kind of confusing. It's just, it's just the way they did it. Okay?
I think so.
Just imagine if it's split upside down.
If you flipped it upside down, then you'd also have to flip the names top. Well, then you'd also have to flip the names top and bottom, right? So what's that? The numbers on the bottom is bigger than top when there are tasks in the queue, right?
I guess that's because bottom is adding more to the queue, so it has to have a bigger number.
Yeah. I mean, if they just chosen a different convention for the names and called one, had to go upwards and reverse top and bottom, it would all still work. But okay.
Bottom is less than the number on the top, and there can't be anything in the queue.
Right. Right. So that line bails out right there because that's just saying there's no work. There's nothing in the queue to steal. And now what we do is we attempt to steal. If we get past that, then we attempt to steal the work. So we take the runnable that's sitting at old top, and we do a cast of old top, old stamp to new top, new stamp, right? And if that cast succeeds, that means we stole the work and we return it. And if it doesn't succeed, well, then we didn't succeed in stealing it. The lights went on and an old man with a rifle came out in the back porch and we ran away. I had a neighbor who had a giant pig going through his yard at night. And he sat on the roof with a rifle for like a week straight, and the pig never showed up again.
I have another question. We need to know like the O notation.
Yes. So you should understand. I mean, maybe not all of O notation that ever existed, because there's a lot there, but Master's theorem is important. It will show up in multiple courses. I want to hit you over the head with it a little bit so that you're softened up for the next class, or if you're already softened up, then that's fine.
Need to know specific O notation for this course.
Okay, so what I expect is that this section under matrix multiplication all has logic that you understand and can follow. Let me get ahead to where I want to be. Yes. Okay. So I expect you to be able to follow this logic. So you can say that, yeah, okay, if I want to break up an n by n processor and find the work on one processor, that's going to be 4 times the work on something of things with half the size in one dimension, right? Plus some order of thing. I don't expect you to be able to automatically know that A1 equal 4A1 by n over 2 plus order 1 adds up to n squared, right? I don't expect you to have the master theorem in all its parts memorized, right? But I expect you to be able to understand how you got the recurrence relation. And so that's for the addition one. And that's the A infinity path length, right? And you remember that the concept here is the T1 over T infinity is our speed up. Our maximum speed up, actually, but yeah. And that should all make sense to you. And actually, these two kind of make sense anyway, right? Because if you want to look at the amount of work in a you want to look at the amount of work in computing the addition of a matrix, right? That's n on a side. It's obviously n squared. You're adding up n squared things, right? And if you're looking at the A infinity path length, because you're decomposing it by halves, right? If you decompose anything by halves and add 1 at each step, that's a log, right? So in some sense, these are pretty easy. There's one of these recurrence relationships that that should be familiar to you from 1351. Do you remember what it is? And not from 1351. There's not a bunch from 1351.
Did they cover these on that?
Yeah, we covered trees in that course, but what I'm thinking about is Q sort and merge sort. Do you remember it from that? Yeah, so you have AN, right, equals 2 times AN over 2 plus order n. And that gives you n log n by magic, which is another way of saying by Master's theorem. There are ways of working it out, but it's work. All right. Does that answer the questions on this stuff? Right. Okay. But does that answer your questions on that handful of slides? Okay. Barry.
We'll need to know about chapter 9 for the next quiz test.
Well,
Really? Yes. Well, I missed that.
at some point,
But we will again.
you will have a final, and then you will be asked about everything, all the way back. Right? Yes. Yes.
Insane.
I'm sorry. I do expect you to actually have learned the stuff. Yeah, it's a college course. But yes, it's cumulative.
ABA stand.
It doesn't stand for anything. It's sort of the idea is something changed and then it changed back, and you look at it and you think, oh, everything stayed the same, right? So in this case, what we're looking at is the top pointer, right? And what I'm doing is I find a value for the top pointer, and then I do a compare and set from that top pointer to a new value. Now, in between my reading of that top pointer and my performing the compare and set, I could have gone to sleep for a while. And while I was asleep, the top pointer could have moved and then moved back. And so if you look at, where was it? Was 125, right? Yes, but 125 is the slide I need for what I'm trying to tell you. So what happens is, on this line here, right, you grab a task out of there. And then you do a compare and set from old top to new top. Now imagine the stamp start here, right? I do a compare and set from old top to new top. And in between my getting this task off of here and my performing the compare and set, old top could have increased and then decreased again, right? It could have done all kinds of crazy things, but my CAS is only checking that it has the same value. And that can get me into trouble. And that's called an ABA problem. Because it went from A to B and then it changed back to A. Because what I'm going to do as a result of this CAS is I'm going to run this task that I copied from here. And if the pointer goes down and then back, right? There's going to be a different task in there by the time my CAS succeeds. So I will be running a task probably that somebody else already ran, and I'm failing to run whatever task was there. So a task that was run already will run a second time, and one of the tasks that was queued won't run at all. That's what will happen if I don't do the stamps. And that's what ABA problem is about. Yes. It's because
Index it. Guess it-
the index into the queue, unfortunately, is not an adequate identifier, right? I guess what I could do, I mean, there's a dozen ways you could solve the problem of that's presented by the ABA here. Something else I could do is I could allow top and bottom to grow without bound. And I could say that they refer to the position in the array that's given by the modulus. And I could just make sure that I push bottom fails if it tries to put too many things in. I could write the thing that way, and then I wouldn't need the atomic markable reference. There's probably a billion different ways you could solve this problem. However, the way they chose to do it in the slides is with the atomic markable reference.
Clarify, it's all about like thread pools right now,
Mm-hmm.
different threads. Basically, instead of assigning individual threads explicitly, you have just a pool of tasks.
Right, you have a pool of workers.
Okay, so this is just one stack that all the threads share from. And
No.
this is the thread.
No. This queue belongs to one thread, one worker, right? And that one worker has access to push bottom and pop bottom.
It's for busy workers. So if one is done, it can.
Right.
That's
So the push bottom and pop bottom are for the queue that belongs to the individual worker, and the pop top is so that one worker can steal from another.
Oh. So that's why the numbers are growing down.
Well, I mean, that's just a convention, but yes.
Can you go over slide 131?
Can I go over slide 131? Take work. Pop bottom. Okay. So if bottom is equal to 0, then we've got nothing in the queue. Otherwise, what we do is we decrement bottom, right? And then we assign whatever was in there to runnable R. Now we do our same game with the stamps. The difference here is we have new top is equal to 0, because if we wind up having to do a CAS, that means the queue is empty, and so we're resetting it. Come on, you can. Okay, so if bottom is greater than old top, right, that means there's like more than one thing in the queue. So I don't have to pay CAS to steal this task, to use this task, because nobody's fighting me for it. So I can just return it and I'm done. On the other hand, if bottom is equal to old top, then I'm potentially fighting someone for this. And so I'm going to set bottom equal to 0, and then I'm going to try to CAS old top to new top. Does it make sense?
Anytime you want to fight over something, you're going to use a CAS.
Right. And at the end, I'm gonna set the even if I lose the CAS, I'm gonna set the new top and the new stamp, because the queue is now empty. because I just fought over the last task. So whether I won or so even if I lost it, the queue is now empty. The stamp is just +1, like always.
Why are we setting-
Because if we fight for if we're fighting for the last task, and whether we fail or whether we succeed, the queue is now empty. I know the queue is empty because I, as the one who's calling pop bottom, am the only thread that puts work into this queue. Right? So I know when I failed to get the last task out that there is absolutely nothing in there, and I can reset it.
So is this all part of the if bottom equals 0?
No, there is no if bottom equals 0 is that's just the first line. That just returns immediately. If bottom equals 0, there's no work. That just returns immediately. Only if bottom is greater than 0 does anything else happen. Right? If bottom is equal to 0, there's no work, and I just return. Because remember, bottom is greater than or equal to top, right? You can raise your hand.
Just wanted to on that, do you show where the queue is stacked? Queue is stacked? It's queue, right?
There's a queue.
Yeah. Do you show where it's updated, where the thread updates? It pushes?
Yeah. I think it's just a little earlier here.
Is that it?
I think. Yes, there it is.
Oh,
It's long and complicated, as you can see.
I'll have to study on my own and we can skip that.
Well, I mean,
No.
Okay, so do we only set new top to 0 if it's the last thing? Like if you pull the last thing out?
yeah, that's the only time we do that. Well, or if someone pulled it out, right?
I think that's where I was confused, because I thought we were doing that every time.
No, only the last time. Because what happens is, right, normally with pop bottom, right, hopefully a lot of times I'm exiting right there. Right? Without paying CAS.
So all of this is sort of handled for us by default whenever we use features.
Yes. There is some implementation of work queues that already exists in Java that you just, when you use the executor service, it just hooks you up with that. But it's useful for you as gurus of parallelism to understand how this stuff works. Work balancing. Okay, so this is something that we don't put a lot of emphasis on, but it's a bit of a simpler way of handling the work balancing problem than work stealing. And what we do here, right, is we get our running task from a regular queue, not a special deck like we had before. I hate that it's deck and not DQ, by the way. I hate that the pronunciation is deck and not DQ, but it is.
I'm glad to find that.
DQ is wrong.
So
Right in my head, and that's all that counts.
Yeah, okay, well, that's not actually how that works. But anyway, So I get a task out of there. If it's not null, I run it. And then what I do is I get the size and I take a random and I get a random number. And if that random number is equal to the size, so that's a 1 in size chance, then I pick a victim, which is some other worker, right? And because it's, you can get into deadlock if you don't have a standard ordering to your locks. That's what we do here. We're going to lock both queues, but we're going to lock the lower one before the higher one, right? So that we don't deadlock. And then we're going to call this balance method. And what the balance method is going to do is it's just going to equalize the number of tasks in the two stacks. It'll just move one from one to the other until they're about the same size. Well, it seems less complicated than what we just went through with the pop bottom and pop top and push bottom. Okay, well,
Like there's an outside force and there's different sizes.
Yeah.
It says
yes, yeah.
The right number, it just shuffles and redistributes all of the tasks.
Yeah, it's just randomly shuffling and redistributing tasks with a certain chance every time. And that's just how this one works.
what if the tasks had to be completed in some type of order? Does a shuffle like to save that?
Well, you really if your tasks have to be completed in a certain order, then you're in trouble because there's no guarantee of that, right? When you submit tasks to a pool, if I submit task 1 and 2 to a pool, they could each go to different threads, and then there's no guarantee which one will execute first. In principle, they could, right? So you can't, if you're submitting tasks to a pool, you're not counting on them coming back in a certain order. That's just given. This is quiescent consistency.
It's like you have like Fibonacci
Mhm.
in the example from the book. They have
Right.
the futures from like the left and the right. And there's sort of like a tree there.
Yeah, but we're not counting on an order, right?
No.
So what happens is, so here's our Java futures, right? So here's our Java futures code. And what happens is, right? We call this future. We do the submit to the executor of this future, right? Then we just calculate this one in place. And then we wait for that first future to be ready. We're not planning on any, we don't know what other what other tasks have been submitted in the meantime, or whether they come back first or second. At this point, we don't care about that. We just want to know when this one gets back.
So even though that future sort of called other futures, it
Mhm.
doesn't really matter so much. It's just
So
getting
so what's happening is this future is going to create other futures, but there's a dependency there, right? One task is going to depend on the other. That's just handled, yeah. If I can remind you, we had a thing about that in the beginning.
giant tree.
It's the giant tree. Where was the giant tree?
It's like
It's
It's like-
there. It is, right? So there's my giant tree of Fibonacci, and how parallel is that, right? And we counted that up, and we counted 17 units of work, and then we looked for the longest dependency path through there, and that's T infinity, right? And in this case, it's 8. So that's what's going on there. Some of those tasks depend on other tasks, and that's just going to naturally force them to finish first. Next question. You believe you're out of questions?
I believe not. So how much more are we gonna have to? How much will we have to know about the concurrent linked list where you have like the lazy and the optimistic and all of that? You have to know each and every one of those in detail.
I think you should, well, it depends what you mean in detail. Can you write it from memory? Probably not, but I think that, okay, so the lock free one, I could not write that from memory, right? I might be able to look at it and say something or other doesn't belong there, but I only have a general idea in my head of how that works at any given time. And like right before I lecture, I work hard at it, and then afterwards it starts to fade, right? Because that's a tricky one.
Lot.
They did, right? So this is the thing with any lock-free algorithm is they're tough to reason about. They're tough to implement. They're tough to get right. I expect you to know certain things about it, right? So I expect you to know, for example, in the lock-free list that we mark things when we remove them, and then when we walk through them with the find method, we clean them up, right? That's a thing that we talked about. And that's a high level point, right? I expect you to know that. I expect you to know that the lock-free one doesn't contain locks. I expect you to know that the lock-free one and the lazy one contain a marked bit, right? They use a marked bit to logically delete nodes as opposed to just physically deleting them. I think the code to the lazy list is probably simple enough that you should be able to reproduce it without trouble, right? There's a field that you put as marked, and then you swing the pointer, and that's how you delete, right? And a similar thing with add. And the idea with the lazy one is when you find the pair of nodes you're looking for, you lock them and you make sure that none of them are marked and that the predecessor still points to the successor. And then you can do your adds or your deletes or whatever you want to do, and it'll all work. You don't have to retrace. Optimistic, I expect you to know that you have to do it twice, right? First you go through, you find the pair of things, you lock them, and then you retrace it to make sure it's still the way you thought it was. So you should know these kinds of basic things about them, right? But there are limits, as I say. Knowing how to reproduce the lock free, that's just a certain level of autism that you're not required to have.
All right.
Lazy method, fill in the blank code.
Yeah, there was.
It was
But
pretty,
it was probably a,
yeah, it
It
wasn't
wasn't
like
that bad.
anything
just
like
got
serious. It was just,
I remembered it like after you guys were reviewing, it was something that I don't know if we violated.
yeah, I think it just asked like, do you know how to remove now event?
There was something about the reordering of pointers, maybe.
Yeah.
Okay.
Yeah. So there's just a general rule. I mean, some codes are too complicated for me to expect you to know them all. I mean, like this push top and pops top stuff. I think it's really interesting, right? And very very clever how it works. I expect you to know what ABA is, right? I expect you to know how the push bottom method works. That one I think is simple enough. You should know how that one works. This one is I wouldn't expect you to be able to reproduce this. Yeah.
A little bit unclear to me is like, so we have the stealing work and the random distribution, right? So are those combined? Are those the same solution, or
Those both solve the same problem. They're two different ways to solve the same problem. And whether you could make them work at the same time or not, I think not, right? Because if you're the work dealing, right? The random redistribution was based on locks. And this code here, the pop top and pop bottom and all that, knows nothing about those locks. And they would interfere with each other. As written, they would interfere with each other. Right? Now, maybe if you rewrote this push bottom, pop bottom thing to work on locks instead of atomics, and then you did something similar with the other thing, it might be possible. But I guess for me, I tend to like the push bottom pop top pop bottom solution better, because it's lock free, right? Yes, it's not so easy that I think you could reproduce it from memory on a quiz or a test, but it's a level up from that. But it's the thing is, if you have a set of work cues, you really don't want to be locking or blocking in any way if you can help it, right? And this is a way to not do that.
So the individual threads grab work from a queue and then they put it in their own queue, or is like a manager thread in order?
When you call a pop top, you return a runnable, and when you get that runnable, you run it. You don't just squirrel it away. So you're only stealing it because you're out of work. I had.
Does the work get into the queue?
Well, let me show you what I had a thing for that. Hold on. Let's see if where is my computer's being slow. Chapter 16. All right, so I had this my executor, right? So I had my executor service that I showed you. Let me just remind you how that one worked. So this has a work queue, and the work queue, right, embodies the push bottom, pop bottom, whatever, right? And so what I do is I have this work queue, and then I have my thread this is the thread that an individual worker is going to run. So for all the threads in my worker, I'm going to create this thread. It's all going to do the same thing. So I'm going to set my thread ID, and then I'm going to have this. Then I'm going to call pop bottom, right? And I'm going to get a runnable. If that runnable is null, then I'm going to walk through the other threads, and I'm going to try to do a pop top. And if I get back something that isn't null, I break out of that loop. And if I get down to here and R is still null, then I just do a yield continue, right? And yield continue takes me back up to where I try to call pop bottom. Okay, so if I do get the work though, then I attempt to run it. And that's basically the simplest way you would use something like that, right? So you just get a worker, it sits there in place, it tries to do pop bottom. If it can't, then it tries to steal. If it can't do that, then it just yields.
And so I'm guessing, is there like a method that would allow you to add something to the executor? Or is
Yes, there's a submit, right? Yeah. So the executor has so the executor service, right, is a interface, and it's got a bunch of things in it. It's got, shut down and is terminated and await termination. Submit, right? Submit callable task, and then it returns a future. Yeah. So what I do is I create a future object, and I used a my future. I implemented my own future, and then I called execute. So submit called execute and execute. So submit has a type that it returns. Execute just takes a runnable. So what I'm going to do is I'm going to create a runnable that's kind of like a callable. So it's going to take this callable. It's going to call it and put the result into this future, right? That's how it's going to work. And then I'm just going to return this future. Now, if I go to the execute method, then what I'm going to do is ignore this part. What I'm going to do is go to my work queue, and then I'm going to call push bottom.
That's one thread.
Yeah, each thread, when it calls execute, it's going to call a push bottom. It's going to put it on its own queue because it's the only thing it really can do. Right? It can't, there's no push there's no push top, right? There's no such thing in this setup. So I can't just go give work to somebody else. I can only put it on my own queue. Make sense?
I'm guessing this execute method is in the context of something that has access to its own queue.
Yeah. Well, everything has access to its own queue. I have this get queue command that I implemented, and I think it just calls a thread. Yeah, so it calls queue.get, and queue.get is it's just a thread local that holds a work queue. So each one has a thread local that holds its queue. And so when I submit to my own queue, I just ask that thread local variable for my queue, and then I submit to it.
So something outside of some thread that's outside of this executive service would call submit.
Well, okay, so if you're outside that, you shouldn't be doing things from outside the executor service. The way I rigged my the problem that you're getting at, and which I have been skirting, is that like the executor service has a certain number of threads, but then I have a main application which is a thread that doesn't have a work queue. And so what I did, I have these two kinds of queue. I've got the deck 2, which is the one we've discussed in class with all the complexity that it has, and then I've got simple queue. And simple queue has the same methods on it, but they're all just synchronized. They're all just locked, right? And underneath, all I have is a linked list. And my pop bottom, is list empty, return null, otherwise remove last. Pop top, remove first. Is full, return false. Because it's a linked list, it can never be full. So, and push bottom is just add last. So it's just dead simple and it's locked. And if I'm on the main thread, that's the one I get. So I have my worker queue. Thread 0 is this thing called simple queue, right? And on my more sophisticated queues are for 1 through n. And that way, if when I go to do a get queue, when I go to do a get queue, if I'm not inside the queue, I'll get the one for thread 0 of the queue, and that one will give me the simple queue, and the simple queue is safe for anybody to push bottom on. Make sense? That's how I did it. There's probably a billion ways to do it.
So that execute on or would it still go to here?
It goes to worker 0. Right? So my default is if I'm on the main thread and I don't really have a queue, then I submit to worker 0. That's the way I set it up. Right. I mean, that's sort of a technical detail. It's just how I solved it. And it's, just the simplest way I could think of.
So threads can access their own queue, and if they have more features inside of their task, they can put it on their own queue.
Yeah, they always submit to their own queue.
Main thread, and then
The first queue, yeah. Right. If so, they're all trying to steal from each other before they get any work. They're all just busily trying to steal from each other, but nobody has anything. Bunch of thieves trying to break into each other's empty houses.
That part was missing, like how the outside of the executor.
Yeah, it's really a technical detail, but it's good that you're thinking about these things. I mean, you need a way to solve that problem. And this may not be the best way, it's just what I did. I didn't think deeply about it. I wanted the simplest thing I could do to show you. because I didn't want to, we've already got enough complexity. Unless you think I should make things more complicated.
And really bright up every picture, so.
You know this old Monty Python routine, with my brain hurts? Well, I'll play it for you sometime, but anyway, it's, my brain hurts is the thing. And they have this patient come in and says, my brain hurts. And the doctor comes in and says, it'll have to come out.
Was a graduate class on multi-core programming. How much more complex would it be?
So look, this course is available to graduate students. This is, I consider this graduate level personally, but I think I've got enough like friendliness around the grading to kind of make up for it, right? So let me just remind you about, you remember what was magical about Fibonacci 3, Fibexec 3? What was magical here is that we had no blocking, right? We when we call our futures, right, we have an F call that can happen in, directly, and we have the supply async future, which is this method I wrote up here, and that is I just get a result, which is a completable future, and then on my supplier I call the get method on the supplier to get the value, and then but that value is a future, and then I call then accept on that future. And when that future completes, I use the value to complete this future I instantiated on line 14. And so anything waiting on the result that came back will get triggered when this happens. And because of that, because this is all done asynchronously, right, it could even run in one thread without difficulty, right? None of the methods are blocking. Each time there's a method, I submit it to the queue, and either run it or submit something else, but nothing ever stops and waits for something to finish. Yeah, and completable future has these things like then accept on it. So what I can do is I can just add methods on there that get called when I want to. Let me go over here. I think, did I? Oh, I probably didn't do it. I didn't put a then method on here. I thought I did, but never mind. Yes, that's correct. It's a callback. So the future has to keep a list of the things that are waiting for it. And
This makes sense. Okay, so the supplier is just the previous future,
mhm.
and then.
The supplier is the actual work. It's going to produce a value. In this case, in the case of Fibonacci, that value is an integer. And when I finally call that value, what I do, it's going to be the supplier is going to return a future to an integer. So when I get that future to an integer back, then I call then accept on it. Now, if the future is already completed, then I don't have to remember it in a list. I just call it, right? But yes, it's a callback.
So just async, like in JavaScript, there's this thing like with promises.
Yep.
So promises can do that.
Dot then.
That then, right? And then you ask to call back.
Right. Yeah. So in Java, the type system is kind of screwed up. And so then what that means, and because of that, they have, you have to have all these flavors of then accept, then compose, then run, right? Because we do parameters, we have generic types are by erasure, and so you can't make any compile time decisions on them. And I mean, you can't have methods that are distinguished only. So you can't like have a future integer and a future string as two different methods with the same name because the type system just doesn't allow that. So you wind up with this horrible array of names that you have to learn in order to do anything. I wish they'd made a different decision. It's one of the big mistakes in Java, in my opinion. One of them is autoboxing, and this is another one.
You scroll up one line.
There
we go.
Yeah, so this is a pattern. Oh, so I have a homework for you that I'm going to assign today. And maybe we should just talk about that briefly. I'll just put it up on the board for you. Oh. So here's your homework. So a reduction is a potentially parallel operation that takes a sequence of elements and reduces them to a single value. To do this, one needs an identity value and an associative operator that takes two values and produces a single result. So for example, addition has the identity value 0, and the function AB goes to A plus B. Multiplication has the identity 1, and the function AB goes to A times B. And many other reductions are possible. A generic reduce function would look like this in pseudocode. So I have a function with a generic type of A called reduce, and it has V, which is a list of A, and an identity, which is also of type A. And F is of type function A returns A, right? And this whole function is going to return an A. So that A is the abstract type. It's usually a float or an integer or something like that. So if the length of this thing is 1, I'm going to return the identity. If the length is 2, then I can just call this function with the two values in the list. If it's bigger, what I'm going to do is I'm going to split the list into two pieces, a first half and a second half, right? And I'm going to call reduce on each of them with the same identity and reduce function. And then I'm going to get two values, and I'm going to return the reduction of those two values. Okay? That's the basic algorithm that I want you to implement for your homework. Now, essentially, this is a divide and conquer to create smaller and smaller lists. Eventually, a single value is computed. Your job is to write a reduce function that runs in parallel and returns a future of the value type it is computing, so A, right? Note that your code should run without blocking. The codes on parallelizing Fibonacci that were presented in class should guide your implementation. So you can look at those slides and figure out how to do it. In many ways, this is very similar to Fibonacci. It's just different. That's the ideal characteristic for a homework problem. Similar to something you've seen, but different.
Well, just when we were in fifth grade.
Yes, essentially. Yeah. You would use those kinds of things. You would use then instead of get. Some flavor of then instead of get. All right. Are we ready for the quiz? Yes, we do.
They're not, if we're ready for it.
Well, I just like to ask.
You can choose not to take the